Welcome to quantum mechanics. In this course, we're going to explore how we can describe fundamentally small microscopic particles that make up the atoms and molecules that we know that we use every day when we think about chemistry. You may be familiar with classical mechanics, in which we treat particles using Newton's laws of motion, and we use electricity and magnetism to think about waves or light. And in classical mechanics, we can separate light and matter particles from each other and treat them with these two different paradigms. However, when we get down to the level of atoms and molecules, protons, neutrons, electrons, we find that these two different ways of thinking about the world don't work anymore. And so what I want to do in this video is to give you a sense of why we need to change our model and why we need to think about this in a different way. So there were quite a number of experiments that pointed out that using Newtonian mechanics to describe matter at small fundamental particle level wasn't working. It didn't describe the phenomena, the observable experimental phenomena that people were measuring. So first of all, let's just think about our classical view, where we think about light as being a wave. So in this view, we know that light can diffract. That is a fundamental property of waves, and it can refract, which is also a fundamental property of waves. It doesn't have a mass, so there's no mass associated with light. And because there's no mass associated with light, we think of this as having no momentum associated with it. Remember that momentum is often given the symbol p and is mass times velocity. So if there's no mass, there can be no momentum associated with the light. So the other thing that we think about when we think about light is that it doesn't occupy any discrete space in our world. So if you think about a light wave, it fills the entire room. So it doesn't have a discrete position. It pretty much just occupies the room. There's light in the room, right? And we think about light waves as being able to have any energy possible. So any energy can be associated with a light wave. And when we think about particles, classical particles, they don't diffract, they don't refract, they don't act like waves in that way. They have a mass, they occupy a discrete volume or position, so I can pinpoint where they are. They have momentum that is associated with how fast they're going and with their mass. And they also can have any energy associated with them. So we can have a particle going at any velocity, and therefore it has any kinetic energy. Remember that kinetic energy is 1/2 mass times the velocity squared. So if it can have any velocity, it can have any kinetic energy. So that's how we kind of think about things classically. Particles, matter are particles, light is a wave. But end of the 1800s, beginning of the 1900s, we have a lot of experiments that showed that this didn't work. So the first inkling of this was when people were looking more carefully at light. So an observation of black body radiation which is essentially the wavelengths of energy, the spectrum, coming off of a glowing body, like the sun, for instance, is a black body. So if we just look at the intensity of light that comes off of a glowing body like the sun, and we look at that intensity as a function of wavelength, so a spectrum of the sun, classical mechanics, classical view of light would say that the higher the frequency, or the lower the wavelength, the smaller the wavelength, the more energy, the more intensity we should have. And what actually was observed, so if we think about the intensity as a function of the frequency of the light, classical view would say that it should go like this, but in fact what is measured is that we get something that looks like this. And so the spectrum doesn't match the classical view. So blackbody radiation was one experiment. The photoelectric effect, which you may be familiar with from freshman chemistry, is another instance where we can't explain the results of the experiment using classical mechanics. And you can read more about this in your book. And then something else you're very familiar with is the hydrogen atom spectrum, or really any atomic spectra, which showed that the energy was quantized. And so the light could only have certain wavelengths, and that goes against this classical view where light can have any energy. So these three experiments, and you can read more about these in your book, are all things that showed us that light was maybe could not be described entirely by Maxwell's equations and electromagnetic theory, and that there was something else going on there. At the same time, we found through Young's double slit experiment that electrons could diffract. So diffraction is very much a property of waves. And so if electrons can diffract, then we have to think of the electrons as waves. There are a number of other experiments that show that matter can also act like a wave. And so these things all put together resulted in the notion that we have wave-particle duality. And this is really the heart of the quantum mechanics formulation and model for thinking about small particles. And so because of this, we're going to have to treat the small particles as waves, not as particles. And that is the model that we're going to use throughout this course to try to explain phenomena on a microscopic level.